In this session, we will discuss about group homomorphisms. So this is basically the same homomorphism which we have already studied in the semi-groups and monoids. So what's a homomorphism? Homomorphism is basically a function between two algebraic structures which preserve that structure. So when you talk about group homomorphism, you are actually considering a function which is defined between two groups. Suppose I am taking a group G and also a group H. Suppose G has the operation star and H has the operation delta. So homomorphism is basically a function from the set G or from the group G to the group H which preserves the structure. What do you mean by the structure? The structure in G which is star and also the structure in H which is delta. So it is defined like this. F of, when you combine two elements in G, how will you combine it? F of G1 star G2 will be same as F of G1 delta F of G2. Okay, so the image of the combination of two elements is same as the combination of the image of those elements. So this is called structure preserving maps. For example, our integral has this property. For example, integral of f plus g same as integral of f plus integral of g. So integral of the sum is same as the sum of the integral. So just like that, this is called a structure preserving mappings. Okay, so we have studied many homomorphisms in when we have discussed about semi groups. So it is same like that. So for example, if you consider the group of positive real numbers under multiplication, okay, and suppose you are defining a function from this to the set of real numbers under addition. Okay, suppose I am defining my function as this. Suppose I define f of x as simply ln of x log x. Okay, so you can see that f of x, when I take two elements x, y in R plus, so f of x, y is actually ln of x, y, and this is equal to ln of x plus ln of y, which is actually f of x plus f of y. So you can see that this function, which is f of x is equal to ln x, is a group homomorphism. Okay, so you can also check that they are groups, and also this has this property. So what is a homomorphism? Once again, homomorphisms are structure preserving functions. Structure preserving functions. And what's the condition? F of, if it's a G star to H delta, this is basically notation, there's nothing to be confused here. F of G1 star G2 will be equal to F of G1 delta F of G2. Okay, so we will discuss more examples of homomorphisms when we will consider another session in which we will be discussing examples of groups per se. So today we will try to understand some basic properties or some features of this homomorphism. Okay, the first feature is their identity preserving maps. They preserve many things. So of them, first one is they just a minute. Okay, the first one is they preserve identity. So they preserve identity. So what do you mean by this? Okay, so consider, suppose I am considering the function. Okay, okay. So consider the set G. Okay, so consider the set G with star, and I am going to take another set H delta. These are groups basically. So I am considering a function from this. Okay, let the identity element in G be denoted by the symbol EG, and let the identity element in H be denoted by the symbol EH. Okay, what I mean to say is these are identity preserving maps is that this F will take EG to EH. So this is my G, this is my G, this is my H, this is my F. So this EG will be mapped to EH. So this is the first condition. F of EG will be equal to EH. So what do we mean by that? This means that basically F of EG is the identity element in the set H. How can we prove that? It's very simple. So we have to show that F of EG is the identity element. So you just consider this value. So now F of EG is lying in H. So there the operation is delta. So consider this thing. F of EG delta EH. What will you get? EH is actually the identity element of H. So when you take F of EG delta EH, you will always get F of EG because you know that this is the identity element. Okay, so by a slight manipulation, I can write this as again F of EG is again F of, I am bringing back this problem to G. So this is actually EG star EG. Why? because EG is the identity element in G, therefore EG star EG will always, this is also idempotent, so EG star EG will always be equal to EG. Okay, so this is actually f of EG delta f of EG. This is obtained by the homomorphism property from the step. Okay, so we have now got it as f of EG delta EH is equal to f of EG delta f of EG. Okay, now all these are happening in H, which is a group. Also, since it's a group, there will be cancellation laws. What is meant by cancellation law? It says that A delta B is equal to A delta C, then we can cancel this out. A then B is equal to C. Okay, you can just multiply by the inverses. So using the same logic here, what will you get? You will get that f of Eg is equal. You will get our result, which is equal to f of Eg is equal to f of Eg is equal to Eh. Okay, so basically homomorphism preserves identity. Okay, this preserves identity. It's an important result. Okay, not only identity, it also preserves inverse of each element. It also preserves inverse of each element. So what do you mean by that? Okay, so can consider this H, G, consider this H. Okay, so you take A. Okay, so it will have an, since this is a group, A will have an inverse called A inverse. So suppose this f A is being mapped to f of A, or similarly A inverse will be mapped to f of A inverse by this function. Okay, now what I mean to say is that the inverse of this f of A will actually be f of A inverse. So the inverse of A is A inverse, and also the inverse of f of A is basically f of A inverse. So f is preserving the inverses. So in other words, if I write mathematically, f of A, the inverse of f of A is nothing but f of A inverse. Okay, so this is the next result. So it will also preserve the inverse elements. So before we try to understand that, what do we mean by inverse element? So in G, let me try to write. So it is basically A star A inverse will be equal to EG, which is equal to A inverse star A, right? So the inverse of f of A, suppose I am just writing it as maybe some k. So the inverse of f of A should also have this property, right? What is the property? F of A star f of A inverse will be equal to E of H, okay, which is same as f of A inverse star f of A. So then any element which has this property will be the inverse of f of A. Okay, so let us try to prove this result. The inverse of f of A inverse is actually f of A inverse. Okay, so how will you prove it? So you just consider this quantity. Let us consider f of A delta. Okay, so in G, H, I'm sorry, H we have the operation delta. So f of A delta f of A inverse. So what is this? By the homomorphism property, I can write this as f of A star A inverse, right? Okay, now what is f of A star A inverse? A inverse is the inverse of A, so I'll get this as f of EG. Now already we have found in the first result that f of EG is basically EH. So now I have got that f of A delta f of A inverse is equal to EH. So similarly, using the same logic, I can also compute f of A inverse. So f of A inverse delta f of A, using the same logic, it will be f of A inverse star A, which is nothing but f of EG, and it is equal to EH. So now we have found that f of A delta f of A inverse is equal to EH, and on the same way f of A inverse delta f of A is also EH. Okay, so what does that mean? It means that actually f of A inverse is the inverse of f of A. So what do you get? You have a set G, you have a set G is there, okay, and H is there. Now you have taken element A, take its inverse, and when this homomorphism acts, what happens? This will become f of A is this will become f of A inverse. Now this results tell you that since the inverse of A is A inverse, on a similar note, the inverse of f of A will also be just f of A inverse. So they are preserving the inverse elements also. Okay, so they are preserving identity, they are preserving inverse elements, and also they also preserve powers. What do you mean by that? For example, if I take A square, that is A star A, this will be mapped to f of A square, which is actually f of A delta f of a. You can just try it. It's the same logic is being applied here. Similarly, if I consider a n, where a is been combined n times, it will also be mapped to f of a n times. So please try it. Try to prove it. It's very simple. So it's using the same property of homomorphism. You can prove that also. Now let us go to an important result. So now we know that it preserves identity, it preserves inverses. On a similar note, it also preserves subgroups. It's a very important result. So it also preserves subgroups. So what do you mean by this? Okay, so this, suppose this is my G, and I have a subgroup in G called S. It's a subgroup. It contains the identity, it is closed, and everything else. Okay, so and again I'm considering the H. Now if I act f on this S, I'm just taking f of all elements of S. I'll be getting actually f of S. Okay, I'll be getting a set S called f of S. So what I mean to say is that f of S is actually a subgroup in H. So a subgroup in H. Okay, so we are going to say that f of S is actually a subgroup in H. Okay, so for that what should we do? So by the subgroup characterization, I have to show that actually the identity E of H is lying in f of S, and also I should show that for every element in f of S, for example if I take f of a, I should show that its inverse also should lie in f of S. Okay, only these two requirements are enough to show that it's a subgroup. So I should show first of all that the identity is layer in f of S, and also for every element f of a, its inverse is also lying in f of S. Very simple. Okay, so how will we show that identity is lying there? So first of all, S is a subgroup in G, so S will be containing EG, the identity of G. So if I take f of Eg, it will actually be lying in f of S by definition. It will actually be lying in f of S by definition. On what is f of Eg? It is nothing but the identity element of H, which means that it is there in f of S. So our first mission is accomplished. The identity element of H is already there in f of S. Okay, now you take an element f of a in S. Okay, actually then I have to show its inverse is there. What's the inverse of f of a? It is f of a inverse, which is nothing but f of a inverse. Already have done this in the previous result. Okay, now since f of a is there in S, we can also say that a is there in S. Since f of a is there in f of S, we can say that a is there in S. That's why it became in the came in the image set. So since a is there in S and S is a subgroup, what can I say? A inverse is there in S. Okay, so similarly, so from this what can you get? That means f of a inverse is there in f of S. Okay, now what does this mean? So when I take an element, its inverse also will be lying in that set. Okay, so I took an element in f of S, and now we have demonstrated that its inverse is also lying in f of S. So f of S contains the identity element and also the inverse of each and every element. So what does that mean? That means f of S is a subgroup. So that is, homomorphism also preserves subgroups. So what's the property of homomorphism? It preserves identity, it preserves inverses, it preserves powers, and now it also preserves subgroups. So it's a very important property which actually preserves the structure and also its associated features. Okay, and a special type of homomorphism is also called isomorphism, which we have dealt with earlier. What's an isomorphism? It's nothing but a homomorphism together with a function, together with the property of being 1, 1 and on. Okay, so this is a homomorphism. We'll see more examples of isomorphism in the next session. Thank you.